Hello everyone, I'm Akash Tiwari, a graduate student from Texas A&M University, and my talk today is on a method of unsupervised spectral band identification for the problem of process change detection. In recent years, manufacturing machines have been increasingly sensorized for process quality and machine condition monitoring. However, being able to detect the anomalous conditions requires effective analysis of the data stream obtained from the sensors. For example, consider the following two vibration time series signals collected from a polishing process. These were collected from the same polishing cycle but at different times. Now, simply by observing these time series signals, it is hard to discern any difference that may exist between the two time series signals. A clearer picture of what is happening in these time series signals is obtained by looking at the frequency domain representation of these signals. The spectrogram resolves the single time series signal into several frequency channels spread over time. This representation is more effective as it allows us to provide a physical interpretation of the process based on the energy in the frequency bands. More specifically, only a small fraction of the frequency channels capture the changes in the process condition. The critical question we will have then is what frequency channels should be monitored? And an open challenge here is to identify a compact subset of frequency channels that can amplify the contrast in the changes that is taking place during the manufacturing process. Let us consider an interesting analogy to our problem. Consider two birds, a chickadee and a nuthatch. Let us listen to how they sound. First, we listen to the chickadee. Now, we will listen to the nuthatch. I'm sure everyone here would agree that the difference in the sound is apparent to the human ear. Now, suppose someone asked you to explain the difference in the two sounds. I would imagine that you will be explaining the difference in terms of the pitch or the frequencies of the sound. Now, looking at the spectrogram, the differences can be even more clearer to the eye. From the spectrogram, we can answer the question of which frequency channels show the largest contrast in distinguishing between the two bird sounds. Now, with this understanding of distinguishing the bird sounds, we bring the intuition back to our manufacturing process. Consider the spectra here. This is a vertical slice of the spectrogram. The horizontal axis here represents the frequency, and the vertical axis here corresponds to the energy. There are three spectrums here: the spectrum from the normal process in blue, the spectrum from the anomalous process condition in red, and the difference of the two process spectra, which is in black. We ask a similar question here as we did for the two birds. Which frequency channels show the largest contrast between the normal and the anomalous case? By observing the spectrum, we can roughly mark out three regions A, B, and C that show the difference between the normal spectrum and the anomalous spectrum. We can consider the three bands to be representative of the phenomenon leading to an anomaly, while the other regions can be considered to be dominant. However, in real life, it will be very hard to manually identify these bands that show contrasting changes. Therefore, we need an automated, unsupervised way to determine such bands. One of the simplest approaches is the fixed size spectral binning, where bands of uniform size are considered. However, this approach may not be optimal. For example, two immediate issues can be observed from the illustration here. Large band sizes tend to mix signal components from dormant bands, which reduce the signal to noise ratio. Similarly, small bands reduce the contrast and cause significant variations in the energy content from sample to sample. Thus, we have an open problem here on how to bend the frequency channels so that we can obtain the best contrast between the normal and the anomalous process spectra. Prior approaches in binning of frequency channels can be placed into three categories. In the first category of fixed size binning, binning approaches are inflexible and suffer from problems discussed in a previous slide. In the second category of adaptive binning, bin locations and bin width are adjusted based on the peak locations. In the third category of minima-based binning, The band size or bandwidth are determined based on the location of the minima adjacent to a peak. In these methods, the binning of the frequency channels relies on the shape of the spectra and not based on the contrast between the two spectra. However, method 4 in category 2 considers binning based on contrast, which makes use of filters. I will now get into our method of unsupervised spectral band identification. Our method can be considered to belong to category 2, which makes use of filters. In searching of the appropriate spectral band, we start with an initial filter and search for a filter that results in frequency bands achieving best contrast. The collection of filters is called a filter bank. In our case, we consider box filters. Consequently, the filter bank is defined entirely by the vector alpha, containing the location of the start and the end bands, and the filter is defined by H. The problem of determining the spectral band now becomes the identification of the vector alpha, which results in the frequency band E that attains highest contrast in terms of classifying realizations of spectra from normal or the anomalous cases. Here, we assume that the resulting frequency bands are independent realizations of identically distributed mixture Gaussian random variables with K mixtures. For our problem, we have two classes, the normal class denoted as class G and the anomalous class denoted by class B, following the distributions as shown. To explain this using the spectra on the right side of the screen, here several realizations from each class are plotted. The frequency on the x-axis is first converted to the energy bands E using the filter bank. In the transformed spectra, the normal class G in blue is modeled by the top equation, and the anomalous class B in red is modeled by the bottom equation. We represent the Gaussian mixture model parameters that fits the data by script M. A more formal description of the problem can be given as follows. The contrast of the features for a fixed alpha is defined by the Gaussian mixture model fit for the data for this fixed alpha. Identification of the GMM parameters is based on the maximization of a likelihood-based criterion. This criterion is captured by the function Q, which is a function of the data and the model parameters to be estimated. The feature with the best contrast is achieved by jointly solving for the best mixture model parameters M and the best alpha. Now, I will outline the numerical procedure that attempts to achieve this joint maximization. First, the spectra is developed from the time series. Following this, the filter bank parameters are initialized as bands of uniform width and is applied to the spectra to obtain the frequency bands. Next, we fit a mixture discriminant analysis classifier, which is based on the GMM assumption of the data. Then, a stopping criteria based on the improvement of the function Q, if not satisfied, will result in update of the filter bank parameters. The loop then continues iteratively by changing the filter bank and developing a new classifier in every iteration, which stops when the criterion is satisfied. Factors affecting the performance of our method include the sample size n, the separation distance between the Gaussian centroids ρ, and the number of iterations the EM algorithm is run for. These factors have an overall effect in the estimation of the model parameters. For example, with reducing separation ρ between the Gaussian centroids, the sample size requirement and the number of iterations required increases to be able to converge to the true estimate. The effect of these factors is captured by the following theorem from a recent work this year. In the first part of the theorem, we see the ratio of n over log n is inversely proportional to the squared separation of the Gaussian centroids. In the second part of the theorem, the convergence rate is given as a bound for subsequent iterations. This bound gets tighter as the sample size increases. We used a simple numerical example to study the theorem. We consider the true distribution F star with the centroids separated by ρ. We consider the distribution F with unknown centroids μ1 and μ2 to be estimated. The effect of separation ρ can be observed in the top left plot. As the separation between the Gaussian centroids increases, the number of samples required for convergence reduces. More specifically, the ratio of the sample size over its logarithm is inversely proportional to rho square. The convergence of the centroid estimate is illustrated for the case of rho equal to 0.5 in the bottom left plot. We see that for a sufficiently large number of iterations, the EM algorithm converges to the true estimate. The number of iterations required for this convergence is guided by the bound in red. For our numerical example, the theoretical bound is given by the right-hand side expression in red. The theorem, therefore, can guide us in choosing the number of samples required for estimation and the number of iterations to be run for given a certain separation between the Gaussian centroids. In our next numerical example, we mimic the case when band sizes are chosen incorrectly, which introduces additional Gaussian mixing components. Here, we fit lesser number of mixing components compared to the true distribution. Again, we borrow results from a work in 2018. Now, due to the incorrect number of components chosen, the estimates don't converge to the true value anymore, but instead converge to mu bar, which will be defined shortly. The convergence rate here is inversely proportional to the square root of sample size. In this numerical example, the true distribution F star has 3 Gaussian mixing components, with the true centroids being a function of mu star and the separation given by rho. The model being fit, however, has only 2 Gaussian mixing components. As mentioned earlier, the estimates of EM algorithm converge to mu bar, which is the minimizer of the KL projection of F star on F mu. Mu bar will still lie in the neighborhood of mu star, but this neighborhood size increases with rho. The convergence behavior of the estimates is illustrated in the top left plot. The bound at each iteration is given in red and is defined by the equation below. The numerical example tells us that when in real life incorrect mixtures are chosen, we may diagnose this if the resulting estimates remain poor, even with sufficient sample size and iterations, therefore requiring an update of the model. We now shift our focus to the application of the method to detect anomalies in a polishing process for ceramic balls, which is of immense strategic importance. The polishing of balls involves very long cycle times of up to 24 hours. Such long cycle times increase the risk of anomalies. The balls are polished in batches with several other balls. During the polishing of these balls, cracking of the balls can occur. These cracks can further develop and result in fragmentation of the balls, leading to ball debris. Debris from the balls can damage the entire batch, resulting in loss of valuable time. Such anomalies can be detected in the development stages of the crack by monitoring for activities in the frequency channels. This can allow us to prevent damage to the batch. The data for the polishing process is acquired through the following steps. During the polishing process, the accelerometer signals attached to the polishing machine is amplified and is downloaded to the local computer through a data acquisition system. The local computer receives the data in MATLAB analog input recorder. To detect anomalies in the acquired signal, a data frame is developed for the classifier in our model based on the spectrogram. We consider the anomaly to occur between the start and the end of the process. As a result of the anomaly occurring in between, the process spectra at the start and end will be different. In this spectrogram, the start and the end of the process are represented by the black bands. Ti refers to the timestamp at the start of the process, and Tj refers to the timestamp at the end of the process. As a result of the anomaly, the process spectra at Ti and Tj will be different with respect to the energy content of the corresponding frequency bands. We sample 5 minutes of the spectra from the start of the process corresponding to 600 samples, and 5 minutes of the spectra from the end of the process, which again corresponds to 600 samples. The data frame for the classifier then looks as illustrated here. The energy content in the frequency bands are our features. The start and the end classes are labeled as 0 and 1 respectively. This data frame is then used in our method. We now compare our results to the case of uniform band size. The most contrasting uniform bands undergo change in their size using our method. The change for each of these bands are illustrated in the rightmost column. When comparing the performance in classifying the anomalous and non-anomalous cases, the non-uniform bands outperform the uniform bands in terms of the classification accuracy. Specifically, the adaptive bands introduce an additional 3% of classification accuracy. We now return to our original channel of the acceleration time series signal. Now it is difficult to judge from the time series signal alone what changes take place during polishing. We now see what changes the most contrasting bands identified from our methods have captured. First, the bands are able to capture drifts taking place in the process. Second, the bands capture sharp energy peaks, which possibly indicates the time when the anomaly takes place. These observations clearly indicate that our method is able to extract bands which capture the changes occurring during the process. Thus, based on the behavior of these identified channels, process monitoring systems can be developed to detect anomalies in the ball polishing process. Summarizing this talk, following are the key takeaways. We formulate the problem of optimal binning as a search problem where we search for bands that hold maximum contrast in the normal and anomalous process polishing conditions. The bands are searched adaptively using a numerical procedure which places a Gaussian mixture model assumption on the data and fits it using an EM algorithm. Using recent theoretical results, we guide our choice of sample size selection and number of iterations for the EM algorithm. The obtained bands significantly enhance the contrast between normal and anomalous cases. These bands also have a 3% improvement in classification over the bands obtained from the uniform binning approach. I would like to finally express my sincere gratitude to our sponsors, especially Lawrence Livermore National Labs and our research associates, including Bhaskar, Suhas Bhandarkar, Chantal, and Sean Maitu. Thank you.